Okay, so hello, everyone. Um,
Hi, yeah.
so this is the first in a series of podcasts, I guess. I don't know what to call it. Where I'm going to like introduce some very tangentially related topics from physics, in a way that wouldn't require you to have any background knowledge beyond like I don't know, like calculus, like university calculus. So like yeah. So I'm just going to assume that you just know what a I don't know, at best you know what I like you need to know what a partial derivative is. That's pretty much the only thing you have to know. And I'm also I don't really I'm not going to really care about getting to any important or cool topics quickly. I'm just going to like just have fun with the math. So yeah. Um.
Yeah.
So yeah. Chen Hao's been studying and teaching quantum field theory these days. What do you think it's like? Like, what is your
Oh,
take on quantum
um,
field theory?
so the way I approach a class is that I from my overall experience so far, when I
Yeah.
started learning QFT, I started with canonical quantization, right?
Yeah.
Canonical the canonical method. Only towards the later part of my physics life that I found out that the Feynman path integral is is a very convenient way to um
Yeah.
reach the more interesting topics like gauge theory and like the funny pop-off method. So in general for QFT, there are two, for me, I see it as there are two main paths to quantization. Of course, barring the BRST and geometric kind, but I think for beginners, there's two main paths.
Yeah.
Um, and so in my QFT lessons, I try to go both paths simultaneously because
Yeah.
yeah, I feel like the path integral gets you to things like the Feynman diagrams very quickly, very easily
Yeah.
with just like a Taylor expansion, whereas the canonical method takes longer. It needs to introduce the S matrix, and then it needs to we need to touch on like the LSD reduction formula
Yeah.
as well as a Wick's theorem before we can actually do the Feynman diagram. So in my lessons, I'm going to try to approach both of them at the same time. So yeah, that's my general take on it. We wanted to discuss about the different pictures, right? Because
Yeah. Yeah. The
yeah,
different pictures. That is actually a fun topic and an important
yeah.
topic.
How about do you want to start talking about the different pictures? So
Well,
maybe I can tell you what I know.
yeah. Maybe you could explain what you know first.
Sure. Okay, so okay, so for the different pictures, because most of us would come across quantum mechanics via you can see my screen, right? Yeah, because most of us will
Yeah.
come across quantum mechanics via the Schrodinger picture, where we have the wave function with the wave function that evolves according to time as follows. Um, and so initially, when you come across the three pictures of quantum mechanics, it may seem like Schrodinger one is um, the more fundamental picture, but um, I think it's important to take a step back and actually realize that in quantum mechanics, the 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 calculations we do in quantum mechanics mainly depend on mainly evolve mainly revolve around calculating expectation values of operators. So, for example, uh, if we want to measure the position of the particle, we take the expectation value of the 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 position operator with some state psi, and they'll be taken by this. Or if we want to take it, we want to do a trace across all the states, then that would be a sum of all the states. And something like that. So uh, um yeah, so the more fundamental concept I like to think of it is that the more fundamental concept the is the expectation value of operators. Um, and so expectation value of operators, um, they can change over time as well. Um, and so in general, if an operator A that evolves with time t, there's three ways to the is defined as this value over here, where you have some initial state psi naught, and then you have the operator defined in the Schrodinger picture, and evolve it with these time evolution operators. Then the three pictures just correspond to where you put the brackets around. If you choose to put the brackets around the state psi and the u, then you get the Schrodinger picture. If you choose brackets around the u, a, and u, then you get a Heisenberg picture. Whereas if you choose to split the time evolution operator up, then you get the interaction picture. Yeah, so yeah, that's how I see it. And from the Schrodinger picture, you can obtain you can actually obtain the time evolution operator explicitly in terms of the Hamiltonian. So you go through some procedure and then you eventually get a time order exponential. And I prefer to keep as general as possible because this from the most general definition over here, you can actually obtain the the more specific ones like this one that's often seen in um quantum mechanics textbooks. I prefer obtaining most general one because I see a lot of text obtain it via this way, and then when it comes time to introduce the time dependence, when h is then time dependent, then you need to basically redo the whole thing. So it's clearer to me if I just start from the most general picture and consider everything as special cases. Yeah.
Yeah.
Then similarly, we also do Phison picture, and yeah, and then that comes to the interaction picture. So maybe yeah, what do you think?
Well, yeah, I think uh let me just like explain a few basic quantum mechanics facts first because like I basically agree with everything you said, but like I'm going to like so oh okay, so yeah, my plan is to like literally um explain all this stuff to like someone who has zero physics knowledge. So I'm just going
Sure.
to explain a little bit
Okay.
more about what's going on. I'm going to do this over here.
Yeah,
Okay.
I can see it.
So like so what Chenho what you were talking about was basically about like a very important thing in quantum mechanics and just like physics in general. You were talking about time evolution.
Hmm.
I'm using my mouse to write.
Oh, I see.
But it's totally fine. So like
Hmm.
so time evolution is something it's just a fancy word uh for like stuff changing in time. But
Mm-hmm.
when we usually say stuff changing, normally when we use the word change, it is implied that change happens in time. So I'm just going to say stuff changing. So time evolution is about stuff that changes, which is important because in physics, whenever we do an experiment, we normally just try to look at how stuff changes. For example, people in particle colliders, we start off with two really fast particles that are bumping into each other, and then they turn into different particles. So,
Hmm.
so yeah, that's a change, and people try to like measure what's going on with that. So physics basically just gives you a bunch of rules using which you could calculate how stuff changes in real life,
Hmm.
which is why physics is useful. In quantum mechanics, as it turns out, there are multiple ways to I don't know explain how stuff change. There are multiple ways to look at the same thing. They're all
Hmm.
mathematically equivalent. As Chen Hao mentioned, there are three ways to do this. There's a way to think that the states change.
So just an idea. Do you want to connect? Not connect. Do you want to draw on your tablet? so you can
Can I
connect.
do this
You
on
can
my
just go to the
tablet? That would be great. Yeah,
you
let's
can
do
just
that.
because all you need is a link. You don't even need to join the room. Yeah,
That's nice. Oh, hold on. Let me get to it real quick. So I'll just like, yeah. So yeah, I'll get there.
sure, sure.
So yeah. So there's three ways to look at it. But the interaction picture is more like amalgamation of the Heisenberg picture and the Schrödinger picture, and I think the interaction picture is a little bit annoying. So I'm just going
Mm,
to talk about the what this Schrödinger picture and the Heisenberg picture first, while
mm,
I connect my tablet to this site. So
sure.
uh yeah. So basically, in quantum mechanics, there is this idea of a state. And and a state, what it means is like it's basically all the information about the universe or a specific subset of the universe at a given time is called a state. Um, yeah, and there are also things called operators, which are more or less the particular values which you can measure from a state. So if you have a person in a room, then the collection of all the information about that particular person in that particular room, would be a state. And and examples of operators might be the height of the person, the position of the person, the weight of the person, and so on, things that you can measure. Um, in quantum mechanics, when we discuss change, essentially what is changing is the values of the operators as measured on the state. For example, the value of a person's height, as measured on a particular person, might change with time. But we can view this in two mathematically equivalent ways. One way of viewing it is that basically the state is changing in time. So basically, the person is growing in time. Another way to look at it, which might be a little less clear to understand, is that basically the observables, the operators are changing in time. So the state stays the same. So we just define the state as say the state of the person in the room at a specific time. For example, right now. So that would be um 2023, January 27th, 9:17, Eastern time. So yeah, so we define the state to be the state of the person in the room at that particular moment in time, and we define the operators with time included. So we would define the operator which corresponds to the height of this person exactly 1 year later after now, which is a totally valid way to a totally different but totally equivalent way to, a valid way of doing things. And in this picture, we see that basically the state, because we defined it at fixed time, doesn't really change in time, at least within this framework. But the observables do, because now you have different observables at different times. You have an observable, you have an operator corresponding at corresponding to the height of this person next year, and you have an operator corresponding to the height of this person 2 years later, and so on and so forth. Um, okay, I'm still trying to connect, but yeah. So these two respective ways of thought it's not really a very it's not really a very, I don't know, it's it's just a fancy way of doing the math in two different ways. But people, uh I personally prefer to consider operators as changing in time and the state not changing in time, because um I think it's a more neater way to do things. Uh because personally
Mm,
I like I like to work with operators. The thing is, like, if you like to work with a specific thing, chances are you would like to view that thing as changing. But for me personally, I like to work with the more abstract viewpoint of dealing directly with operators instead of like dealing with states. If you're new to quantum mechanics, it might seem more reasonable to deal with states because the concept
Mm,
of the collection of all the information about your particular system uh, seems more concrete than the concept of the set of all possible things that can be observed about that system. But if you look at it from a mathematical perspective, it is much more, it is very nice. It's very cute. It's very clean and very elegant to work directly with the set of all possible things you could observe about your particular system. Um,
mm,
so in this particular case, the set of all possible operators is called an algebra, which is basically some kind of generalized, fancier version of a set with some operations similar to multiplication and addition that you can do on it. So, okay, that's really okay. Let me just connect. No, wait. Okay, I'm getting there. This is only going to take about 30 more seconds before I can connect to the whiteboard. But yeah, that's basically it. Um,
okay, just a
okay,
heads
I'm
up.
here. I
Yeah,
think you
okay,
can.
great.
It's
Uh,
loading. Okay, let's see here.
just a heads up. My internet nowadays seems to be a bit patchy. I think there's something wrong with my internet provider. So,
Oh no.
yeah, if I suddenly disconnect halfway, just know that that's probably the reason.
Okay, I'm back.
Ah, yes, I see. Okay, good.
Okay, so yeah. But anyway, so I talked about states and I talked about operators and talked about operator algebras. Um, so yeah, I'm going to mainly talk about these. Um, so this is just a set of stuff that changes with time. In the long term, right? Like yeah, I mean we could elaborate further, but in the long term view, right? We would like to have some fun, and it would not be fun to explain everything in a detailed way, even when it is not aesthetically beautiful. So an operator algebra, in my point of view, is just a set of stuff that changes in time. Which is this basically means that a set of stuff that is a function of time. And we're just going to look at that and see what's going on about it. Yeah, your internet is a bit slow. Look at the letters slowly appearing on the screen. That's
Yeah,
funny.
I think so.
But yeah, that's totally fine. But now I just wrote all this stuff down, but I have to explain what's time. Now, physics uh tells us absolutely nothing about the deeper ontological questions of what time is from a philosophical sense, but those types of questions are usually better suited for someone else. But physics gives us a really nice framework for like actually doing calculations about time and space. Because if you have time, you also have to talk about space because these concepts are actually pretty similar. Now, a good way to understand time and space is to draw it. So let's draw a two-dimensional space. Let's draw, it's like a piece of paper, and I have a stickman on it. Um, But a stickman is a bit complicated, so we're going to think of something else and consider a point, a tiny ball, I guess, that has zero size that this stickman is playing with. Now, assume that the stickman throw this ball like this, and it moves in like that direction on the piece of paper. A reasonable way of basically drawing this trajectory of this ball is to draw a three-dimensional graph with the time being the y coordinate and the space basically being the x and z coordinates. You know what? Let's just call it x and y. So it's x, y, and t. It's a three-dimensional graph. And if you draw the trajectory of the ball, it will basically look something like this. Which is taking a while to load for you, but there it is. Yeah, so that's basically the trajectory of the ball in this particular graph. We call this the world line in physics. But that's just a fancy way to do it. It's just a curve. It's just a curve. It's just a curve in some kind of three-dimensional Cartesian space. So basically, we've learned that in this, basically, if you draw a graph like this, time and space are practically similar because they both are just kind of axes for this particular space. So we can realize that if we don't need to talk about these things separately. We just need to talk about spaces in math. For now, we were talking about Cartesian spaces, but like, or Euclidean spaces, but like, yeah, we just need to talk about spaces in math to understand time and space. So, okay, so let's just talk about the concept of space. Space is something that is space. This is related to the concept of manifolds. But I'm just going to explain why it would be important. Wow, your internet is really kind of slow. That's kind of sad, but like, hopefully I'm record.
Yeah.
Yeah, but it's fine. Like, I feel like it is necessary to have this type of lag. I like this spontaneity. So yeah. Okay, so we're gonna talk about space. And you can think that space is simple to understand because I just drew it. Space is something that has three axes. Space is some kind of n-dimensional thing, which is reasonable, but sometimes you can have non-trivial space. So this is just a flat piece of paper, which is a type of space that you can imagine inside your head, but you have different things. Oh no, I lost. Wait, okay. What's going on? It says that I cannot connect to the server. Let me try again.
Your tablet.
Oh yeah, I think
Also,
I'm back in. Wait, let me.
great. Also, no worries. I can nowadays my videos I actually edit them a lot more. So yeah, I can always edit out the parts
Yeah,
and make it
I.
really smooth.
Oh, I see. Yeah. Okay. So I guess you're going to upload these to your YouTube channel because my YouTube channel I haven't done anything on it for a while. Okay. Okay. I think I'm back.
Sure. Okay.
Okay. And now you have like the surface of a cylinder. These two are kind of different. So it seems important that you would have to consider both. And there are other things that you cannot comprehend yet. Well, you could comprehend the surface of a sphere, but these are all not the same. You could have a Mobius strip, which I suck at drawing, but I honestly don't care. So like yeah, these are all
Mm,
kind of different. You also have like Klein bottles. These are all fun and fancy things. They're all different, and it would be nice if we could understand most of them or all of them because it seems that these are all very interesting things and pretty to look at. So you can describe this. They all have you can describe these. You can generalize this concept by looking at how these things are similar. And these things are similar in the sense that you could basically cut out pieces of them and they would essentially look the same. Like if you cut out a piece of them, they all look the same. They all so a piece of them looks the same. but the whole thing might look different. So you can realize that you can define a manifold as something that basically has a bunch of properties that have to be satisfied with respect to basically a piece that you could cut out of it. Okay, so I'm going to define a manifold. Uh, the definition is basically the same for any dimension, so I'm just going to define 2D manifolds, and hopefully you can easily generalize to higher manifolds. So if a 2D manifold is basically a thing. It's a thing so that if it's a thing with points in it. It's a thing with points in it. So let's say that P is a point. Then you can just like cut out a piece of the thing so that the piece contains P. Your internet is good again. Nice. Okay, so um yeah, this piece more or less looks like a piece of the Euclidean 2D space. And by Euclidean 2D space, I mean like the usual two-dimensional space of like an X and Y graph. So if you were to cut off a piece of that, it would look similar uh, it would practically look identical to this piece that we cut out of this thing that contains this point on P. Um, so for every point in the thing, there is like a local region that is isomorphic to Euclidean space. That's basically just the definition. Um, uh, more or less. That's more or less the definition. But sometimes you would like to like do calculus on this manifold. For example, right, if your manifold is just like Cartesian space, you just have like a point here, and you have a function f of x and y, you could calculate partial f partial x and partial f partial y. This is a very easy and sensible thing to do. Um, so yeah, but somebody might want to do something different. So they might say, I'm going to make a new coordinate system over here. This is going to be A and B. Could we do partial f and partial A and partial f and partial B? The answer is yes. Like all of these are totally cool. Uh, but things might not be cool when something terrible happens. For example, let's uh, say, let's see, consider some terrible choice of y, x, a, and b, so that partial y, partial a did not exist. Then either partial f, partial y, or partial f, partial a will probably not be well defined. Uh, this thing by saying partial y, partial a does not exist, I mean that this is not differentiable. In that case, either one of these will probably not be well defined. So this is a very annoying situation to work with because there is like no sense of a reasonable definition of a function that is differentiable on this particular manifold. So we would have to restrict to coordinates systems that are differentiable with respect to one another. So we can only work with these particular coordinate systems. This seems like a pretty reasonable way to do things. In fact, uh, it might not be make much sense to do things in a different way if you want to do calculus on manifolds. Um, so okay, so let's now consider an arbitrary manifold, which looks a little bit different from Cartesian space. Um, and say that you have a point P and you have a piece that you cut out um, surrounding this point. So you have this piece, and because this piece basically looks similar to like Cartesian space, you can do the same thing by basically having like coordinate systems on this particular piece, x and y or a and b. You can have these things, but it would be nice. In fact, yeah, it would be nice. It would be necessary to have basically all these types of values existing. So like partial x, partial a, partial x, partial b, and partial a, partial y, and partial a, partial x, partial b, partial y, partial b, partial x. It would be nice to have basically all these values well defined. So we can guess that I think we can guess that it is a suitable way to basically define doing calculus on a manifold as basically taking one point and cutting out a piece surrounding that point and then working with a specific class of coordinate systems such that the patch surrounding that point are basically mapped to these coordinate systems, which are basically um, collections of two different numbers that basically map one to the points on that particular patch. And that if you're going to use a different coordinate system, then basically the map between these two coordinate systems should be differentiable. And also you can consider other cases where you have 2 points and you have two different patches, each surrounding these 2 points, and you have a part where these two patches meet. In this case, you can have a coordinate system for one patch and a coordinate system for the other. They'll meet in this region, and in that particular region, the map between the two coordinate systems should also be differentiable. Because if you don't, then we'll end up with the same problems that we had earlier. So basically, this is what is called a differentiable manifold. A differentiable manifold is essentially a manifold where calculus with coordinate with respect to coordinates makes sense. In this, yeah. So you will, and now we realize, if we were to do a little bit more physics here, now we realize that time and space are basically just coordinates on the coordinates of a differentiable manifold. And this differentiable manifold is basically space-time because it has space and time.
Yeah.
Uh, yeah, I don't, yeah, please ask questions like, I think there are multiple ways, in which, you could ask questions about this.
Hmm. Hmm. Okay, perhaps maybe I'll ask a question. What if so let's say we have a world line on this manifold and
Yeah,
it crosses across two coordinate charts.
yeah,
So how would in general when we have a world line we want to have a differential equation that describes it.
yeah,
So what I mean is that suppose that we have a particle so let's say we have some manifold
Yeah.
And let's say we have a particle that goes across it in this direction.
Yeah.
And because the manifold is described in terms of coordinate patches,
Yeah.
right? What if we have such a situation and we want to find the differential equation for this particle's equation of motion,
Yeah.
then how would one sort of find um this let's say we have a differential equation for this segment of it, then
Yeah.
how do we extend it to we have it individually, but how do we essentially combine the two?
Well, I think like in like in this middle region, the great thing about this middle region is that you could use either this or either one or either two, right?
Yeah.
So you could do calculations with either the coordinate patch of number one or coordinate patch of number two. In your question,
Mm,
basically, we were able to do calculations with coordinate patch number one.
mm,
But the good thing about this particular region is because that since we're able to use either one or two in this case, if we have some
mm,
calculations here, we should be able to basically move the calculation. We should be able to like kind of transfer the calculations to number two by doing some coordinate transformations. This is just like
yeah.
change of variables, I guess, exchanging variables in calculus. And now you have an
Mm,
equation of motion for a region two, which hopefully you can extend to the whole region, whole patch of
uh,
patch two. And you could do this continuously to just kind of get a sense for the whole manifold with like number three here
mm.
and so on. Um,
So it's tying in on the compatibility of charts. Basically, the compatibility of charts condition tells us that we can transfer
yeah,
derivatives of some curve in one patch into
yeah,
another patch, and
yeah,
this way, whichever path, whenever it exits it, because we know that the entire manifold is covered by patches, that
yeah.
we are sure that there isn't a point where you have a place where the curve has no
Yeah, where
every
the
point
curve
along the
has
curve.
like a is non-differentiable, or the curve has a weird thing going on.
Mm,
Um,
sure, sure.
I think
Yeah,
I should mention
that makes
that
sense.
you would require not only the first derivative, but you would require like all the derivatives to be well defined.
Mm,
Or else we couldn't do cool stuff. Like usually, it would be nice if we could differentiate if we could take the derivative of a function as many times as we want, and that's usually the
mm,
case for useful models in math and physics. So yeah, that is usually the case.
yeah, okay. Looks good. Yeah. Um, yeah, I think then okay, so how about the tangent space? So there are a few definitions of tangent space. The one I'm most comfortable with is the is the one where we define um functions on so given a manifold, suppose we have a
Yeah,
manifold, and we want to find for every point, right,
yeah,
there's a sense in which there's a tangent plane,
yeah,
and the motivation for defining the tangent plane is that we want to we want to describe a way to uh when with particles on when with particles on the manifold, we want to say like the particle is moving towards this direction.
yeah.
Um, so we want to find a way to describe basically velocity of particles
Right, yeah, yeah,
in a rigorous way. And when we want to define velocity, we need uh velocity is a vector, so we need some sense of vector space where add we can
yeah.
add velocities together to get a new velocity as well.
Right, right. We need a space
Um,
of arrows. Yeah,
yeah, we need a space of arrows at a point.
yeah,
Uh, and that is the definition of roughly we need a definition of tangent space because we want to define velocity.
yeah,
Um, and so uh, the difficult thing is that what is the most natural way to describe these arrows? So the way I see it is um the most natural way to there are a few equivalent definitions. If we just search uh
yeah,
tangent space, we can actually see that there's a way to derive it using let me see, equivalent definitions, formal definitions. There's a way to describe it using tangent curves. There's a way to describe it using derivation, and there's even one about via cotangent spaces. My personal favorite is to define it um using the I think it's a space of um derivations.
Oh, okay.
Yeah, it's probably the space of derivation. Wait, probably let me think. But I feel like it's probably neither of these two. Um,
Yeah,
okay, so how I see it is if so currently when we have a differentiable manifold, we can only define functions from that manifold M
yeah,
onto a real number. We can define yeah. So this is something we can do. It takes a point P on the manifold
yeah,
and it maps it into a real number f of P.
right,
Um, um, so when we have so right now currently we are unable to define the derivative of this function because um yeah we're unable to define the derivative of this function because we just have a point P and it currently has no knowledge of its neighbors. Um, in in some sense, it has no
right. I
knowledge of
mean,
its
I mean, we
neighbors.
could choose a coordinate system and take the derivatives there, which will give
Yeah.
you a bunch of information. But clearly, the way that information is organized is not really that fancy and nice to look at because there are a bazillion coordinate systems that you could choose, and it's hard to see if
Hmm.
choosing one specific coordinate system and calculating the derivatives in that coordinate system really means anything that important. So it would, yeah, as you said, it would be necessary to give some more structure and vectors to
Hmm.
that. Yeah. Anyway,
Yeah,
keep
yeah,
going on. Yeah.
exactly. So the way to circumvent this is that we cannot do derivatives on M directly. We cannot say uh, partial of f with respect to some change in something because there's
Yeah.
but that is exactly where the coordinate patches comes in. So what we do know is that there are functions from M. We do know that there's functions from M to R RD, where D is the dimension of this manifold.
Yeah.
And we know that it's invertible, meaning that we can go from RD to M as well. And
Yeah.
so that means that there is a local coordinate patch, perhaps this coordinate patch that and this maps is homeomorphic to RD.
Yeah.
Um, and from that we can actually and then we have the map from M to R. So
Yeah.
this is the I'll just call it phi. Usually we denote phi for the homeomorphism.
Yeah.
Um, and that would mean that the map of if you compose F inverse um and F, then we actually
Yeah.
get a map from RD to RD.
Right.
Sorry, to R, and
Yeah.
this is something that can be differentiated. So
Right.
uh, what that means is that we can apply what this is a multivariate calculus kind of map. We can do partial derivative of this F uh, phi inverse with respect to each of the coordinates x, um, and this x being part of this RD.
Right.
So I describe mu for every single one of the coordinates, and this actually just means partial with respect to x1, partial with
Yeah.
respect to x2,
Let me
where mu
just
is an index that goes from 1 to d.
yeah. So
Uh,
x1 dot 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 xt. Pew 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 pew
yeah.
pew 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 pew. Like
So this would essentially give us a way to so what this is saying um physically is uh I have a I have a patch over here which is RD,
yeah.
and now I'm saying that if I start from some point, let's say this point, and I move in the direction of increasing, let's just choose one coordinate. Let's say I choose x1, right?
Yeah.
Let's say we are in the coordinate system where x1 is r and x2 is theta. So what I'm saying is that increase
Yeah.
r, and that would increasing r would trace out a curve, right?
Yeah.
Um, starting from this point, and increasing theta would trace out another curve, perhaps let's say like this.
Yeah.
Um, and I mean for concrete realization, if you have the Euclidean plane, then these are if we start from let's say this point, then increasing theta would would, would go in this direction, and
Yeah.
increasing r will go in this direction. Just that now we're on abstract manifold, so the r direction and the theta direction. And essentially we're asking how does this function change as we move along this this increasing R. Um,
Yeah,
yeah. Uh, so so the nice thing about this is that we can actually apply the chain rule. Um, Let me think. So we can actually apply the chain rule. Mm, okay, maybe
right
let's
about
not.
here. Um,
Yeah. I don't know. Do you have any
I think
idea
like
how to
what you were
continue
going
this
for was like
motivation?
something. Wait. Okay, so let me just like wait. Let me just change the equation a little bit. I think what you were going for was like
Sure.
something along the lines. No wait of sum over mu partial x mu. Yeah, I think you were looking for something like this,
Hmm. Um.
which
Ah,
is an equation that is mathematically correct.
I see. So what the R is in this case is in one coordinate patch, right? Then the theta
Yeah.
is in I mean the X is another
Yeah,
coordinate patch, I suppose.
so like you currently have two coordinate systems. One is where you have R data and a bunch of other guys that you didn't really define yet. The other
Mm-hmm.
one is the x0, x1 dude, and you
Mm,
just did like a going back and forth between these two.
sure, sure. Um,
Oh no, wait, yeah. Oh, this. Well, I guess this thing is doesn't really matter anymore. I'm gonna get rid of it.
yeah, okay, let's then, um, hmm, um, I'm trying to um, I'm trying to lead to a definition of tangent space. Um,
Yeah. I mean, like, so. I guess one interesting thing is that it doesn't like you have this idea of basically it doesn't really like yeah. So you have this idea of taking the derivative with respect to the coordinates, which is a nice thing.
hmm,
But you can take this and you can turn it into a different concept, which is the idea of taking the derivative of a function along a curve. Um,
hmm,
and the nice thing about so there are two different things going on here. The first one, I'm drawing this like below the circle. Uh, wait, okay, like over here. So like the first one
yeah,
is basically you have x1 and x2, and then you take the partial of f partial x2, which is nice. But the other idea is you have the manifold and you have like a literal curve going on here. And you
hmm,
literally take the derivative along the curve because you can like parameterize the curve, right? And
hmm,
you can take d lambda f. Um,
right, right,
and if you look at these two different ways of taking a derivative, um, well, they both make sense. They're both legitimate, but the second one is nice because it is intrinsically geometrical in the sense that it is defined with a curve, and a curve is a very reasonable and natural thing to have on a space, right?
hmm,
Curves are nice. So like you could define you can define derivatives on a manifold by defining derivatives of a function on a curve. Um,
hmm,
which is nice. So if you were to so I think we can't if you were to talk about basically a particle, a world line of a particle, and there is a temperature, Tp on every point of the manifold,
hmm,
if you were to parameterize the world line, you could at least calculate the rate of change of the temperature that the particle sees or observes as it moves along its own world line. That's one thing you could do. Um,
yeah,
but
that makes
we
sense.
yeah, but we haven't really uh defined vectors yet. And you
Hmm,
said that the idea of vectors is that you would like to have a notion of vectors basically tangent to a particular point. Um, and the way you can do this is if you were to talk about the definition that you prefer, is that is defining vectors using derivatives. Um, is that noticing that you could basically do a nice one-to-one map between these so-called tangent vectors, tangent arrows, and you can do a map between them and basically these derivatives on curves.
Oh yeah. So what you're saying is that I guess d over dt over d lambda, the
Yeah,
derivative of the temperature along the curve can be thought of as a it because um we can think of it as a d d wait, let me try to uh so dx mu over
yeah,
d lambda and dt over dx mu.
yeah. Let me just.
So this the implication of this is that, oh yeah, there should be a full derivative.
Yeah,
The implication of this is that this is telling us what are the coordinates of the curve. The coordinates of the curve will be something like that. So this is well defined.
yeah,
And this term over here um is telling us along, yeah, it's the previous interpretation where we have the lines of uh for increasing x1, for increasing x2, and so on, for
yeah,
increasing x mu. And this leads to a, in effect, so to emphasize this isomorphism, this one-to-one mapping, um, so for every curve that you have along, uh, for every curve you have in a manifold,
yeah,
we want to define tangent arrows. But
yeah,
why do we want to define tangent arrows? We want to define tangent arrows so we can tell, so we can calculate, right? Given this point and this tangent arrow, which point we want to feed in a point P and essentially um, map it through this tangent arrow, to a point P that is near a P prime that is near
yeah.
P.
And it
Essentially, we
has
want
to
to
and
do
it
this.
has to be near the point because
Mm,
like in Cartesian coordinates you could have like big vectors in the sense that you could have like vectors that are literally a displacement between two uh far away points. And this is for the
mm,
Cartesian case. Because in this case, like you could define the addition of two vectors because the really important thing about vectors is that there's stuff that you can add together, right? But like you could
mm,
define this in the Cartesian usual high school geometry. But if you have but you have like an arbitrary general manifold, and you're really talking about all the possible general coordinate systems. If you think about it, there's no really natural way to define that
a
uh
huge factor, right?
well-defined addition for like yeah for large displacements for non-infinitesimal
Mm,
displacements. So really this p prime near p is really the essence of the understanding what vectors on a general manifold is because it really has to be infinitesimally near p. And the only way
mm,
to really consider that is if you're considering some type of calculus on the curve, right? You have to the only way
mm,
you're going to consider an infinitesimal displacement is by basically calculating some limit of a rate of change as you make that
mm,
infinitesimal displacement, which is essentially just calculus, which is really the
mm,
essence of the mapping over here. Um,
mm,
I guess the reason why some people might find this map a little disconcerting is because the lack of what is not here, right? Because we usually, when we talk about the
yeah.
derivative, something has to be here. But the equation that you wrote over here, um, which is taking a time to load from your side, is basically wait, like I just drew something, it's not showing on the screen. Are you there? Wait a second. Oh, I think the internet connection's a little bit bad on your side. Um,
Hello.
hello. Yeah, I think I got knocked out of the room or something.
Okay. It's okay. I can always edit it. Yeah.
Yeah,
Yeah, sorry, you're saying.
so like if you look at the equation over here,
Mm,
you can see that basically when you're calculating this thing with something actually inserted in here, um, the part that does not change even when you have different functions going in this
Yeah.
position is basically this part. Like
Yeah,
this is
exactly.
the general part.
Mm.
Uh yeah, this is the general part. So we can see that roughly speaking, the tangent arrows here are having a one-to-one correspondence with this general part over here.
Mm.
Um, that being said, this is just a collection of numbers. As mu goes from 1, 0 to d, d minus
Mm.
1, whatever, or 1 to d. This is just a collection of numbers. This is not an arrow. Uh,
Mm.
so so by defining, if we want to define something that is not just simply a collection of numbers, but something that is basically some kind of tangible thing, defining it like this kind of makes sense. So basically, a tangent arrow, we just take a tangent arrow to mean some kind of arbitrary derivative on a curve at a particular point, which is a bit
Mm.
abstract, but it's really the best we could do. Um,
Mm. Um,
and uh, we can say, um, well, what we can ask then, what do these numbers mean? Because you can say that these are basically an alternative way to basically characterize a vector, at least in some particular coordinate system, right? Um,
mm.
but then you can notice that basically, if you have a point P, the partial derivatives, partial x mu correspond to the rate of change of a particular along a particular curve in which x mu changes,
It's increasing.
but
Yeah.
the x mu prime with mu prime not mu are fixed. So it defines a particular curve. And if you
Mm.
define the curve as basically being lambda equal to x mu in this case, then you can see that this is equal to d lambda for this particular choice of curve.
Mm.
Um, So what this tells us is that we can take this, and this can mean a vector in its own. This can actually, we can take this to actually mean a vector, which if I were to write it as an arrow, I could write it as e mu, right?
Mm.
Because this is a vector. I'm just going to put arrows on vectors for now, just to show that they are vectors.
Mm.
So if we were to define the vector v, um, as basically d lambda for some lambda, we can see that v, if you see that, is actually equal to dx mu d lambda and doing a sum over mu e mu, because d lambda, if you apply this to an arbitrary function t, we saw that this is equal to this thing. This was the equation that you just wrote a few
Mm.
moments back. But you can see that this is just equal to acting e mu on t.
Mm.
So now that we have this equation, we found out majestically that these numbers are basically components of this vector in a particular basis expansion, which is really
Mm.
nice. Like this is nice if you think about it. Um,
Mm.
so
Yeah.
now we have the idea, we have the concrete statement of what it means of basically like intuitively understanding a vector as a velocity, because this is basically the components of a velocity in a particular coordinate system, and we just realized that
Mm.
velocity, at least the components of velocity, are basically the basis components of a basis expansion of a particular vector. And so it actually makes a ton of sense to define the velocity as a vector.
Mm. Yeah. There's also that's a great. Yeah. It's not clearer now. There's also the issue of possible uh multiple choices of curves that define the same tangent arrow, which is
Yeah,
where exactly this equivalence class comes in, where we
right,
want to.
right. Yeah,
Yeah.
because like they could have like the same derivative at this particular point, but they could just like go away afterwards. Like
Yeah.
over here I drew a picture far, yeah,
Mm.
below.
Yeah, I
So
see it.
these two
Yeah.
define the same vector at point P. But obviously, if they were to intersect at different points at point Q, they would have two different vectors at Q. But
Mm,
basically, what matters is basically the equivalence class of curves near point P in
mm,
defining the vectors at point P, and not just all arbitrary curves, because that's way too much information.
mm. Yeah. So, okay, perhaps if I may try to summarize what you have said in an attempt to make
Okay,
for the viewer to
just let me just uh,
hi.
uh,
Yeah, I think you might have disconnected from the whiteboard.
yeah,
Okay, yeah, sure. I'm going to try to summarize the discussion in
yeah,
an attempt to make a bite-sized video that it can be uploaded as a like you can think of the previous discussion as as the the just rehearsing, and then I'm going to try to
yeah.
attempt to do it properly, uh yeah, without any like pauses and stuff.
Okay,
So you can just stop me anytime you want to interject any insight, or if
yeah,
there's
yeah,
anything I
sure.
said that's wrong.
Wait,
Yeah.
so are we going to like upload the whole video, or are we just going to like, are
I
you
think
going to edit it?
I'm going to edit it. If you wish, we can upload the entire thing as an unlisted video, and have a playlist for that.
Yeah.
Or I can, yeah, yeah, it's like kind of the behind the scenes kind of thing.
Okay.
Um,
So is it okay if I just like give if I just like ask you to do all the editing for the video because like
yeah, yeah, sure.
so like I'll send all the video clips to you through a Dropbox
Hmm,
folder, and you could just do whatever you want with it from there. Like
sure,
it's up to
sure.
you.
Yeah.
You could do whatever you want with it. So
Okay,
yeah.
thanks, thanks. Actually, nowadays I pay editors to do some of the editing for me.
Oh, that's nice.
Yeah,
That's nice. Yeah, yeah. Just do that. Just give me credit for
sure.
whatever I said, but
Hmm,
with respect to how you edit that, that's up to
hmm.
you.
Okay,
I'll just
sure,
take
sure.
credit
Thanks.
for whatever I said, like just for the
Yep.
contents itself. Yeah.
Yeah, I'll credit you as part of I mean, as a, I'll mention your name, yeah, in there.
Okay, cool. Yeah.
Yeah. Okay, so the idea of tangent spaces, okay, so the idea of tangent spaces of manifolds is that when we have a manifold M, the manifold is just a collection of points. We can imbue the manifold with a differentiable structure that allows us to take derivatives on it. On top of that, the manifold, besides being just a collection of points, the manifold is also covered by a bunch of coordinate atlases, such that every point on the manifold is guaranteed to be in one such coordinate atlas, in
I
one
think you
such
call I
coordinate
think you
chart.
call it,
Yeah,
yeah,
in one
or a
such coordinate chart.
patch. Yeah. The
Yeah,
atlas
okay,
is
sure.
the set of all these charts. Yeah.
Yeah, sure. So the definition of the manifold also ensures that every single point on the manifold is covered by at least one coordinate patch. And the collection of all the coordinate patches is called the atlas. So what this allows us to do is, for each coordinate patch, it allows us to define, for each coordinate patch, we have a homeomorphism between that coordinate patch with r to the d, where d is the dimension of the manifold. Um, by definition. And so the goal of defining tangent spaces of manifold is that now when we have a manifold M, we want to be able to take um, a point P, and we want to say that there is, in some sense, an arrow from originating from this point. And if we walk along the arrow, we want to get to another point P prime that is essentially near P. The difficulty in defining this arrow is that um, yeah, we want to define this arrow rigorously. So um, the difficulty is what to ask. Okay, so we want to define arrow tangent vectors from originating from a point is essentially a vector, and we want to be able to add multiple vectors together. So if I have a vector v from originating from this point like this, and I have a vector v prime originating from this same point P like this, I want to be able to add these two vectors together uh to get a vector. Basically, we want to define a vector space at a point P, which we will write as TPM, and this is a vector space at P. Um, and this might be useful for a lot of reasons because if we have a particle on a manifold M, we want to be able to describe its velocity, and we want to be able to add velocities together to get new velocities. So how do we define this tangent vector? So the key idea is that a tangent vector should be able to get us from a point P and essentially map it to another point P prime near P. Um, but how do we do this when the tangent space lives at point P? So we're actually going to use the differentiable structure on the manifold. And how so? When we are at point P, there can be many curves passing through. Oops, that's a bad drawing. Um, when we have a point P, we can have many curves passing through that point P. When we have a point P, we can have many curves passing through a point P. And each one of these curves is essentially a map. So I'll call this curve gamma. It's essentially a map from R, or we can actually think of it as perhaps each one of these curves is actually a point. Each one of these curves is actually a map from the interval 0, 1 to a point M on the manifold. And by and there's going to be some value in the domain of this curve, gamma um of some value. Let's just call it lambda p, which gets mapped to the point P on the manifold. Um, and essentially, we want to what this curve allows us to do is we can actually take this lambda p and move it by a small amount epsilon, and that will give us a point P prime that is near P. Um, yeah, so we have this curve, we have this definition of curves on the manifold, and we want to define the tangent vector that can bring us from P to P prime near P. So a natural definition of tangent vector is to essentially um our goal is to define a map that is one to one, that for every curve it maps uniquely to a tangent vector, and for every tangent vector it maps uniquely to a curve. There's some issues that we may foresee at the moment, which is that there may be many definitions, there may be many curves that map to the same tangent vector, because if we have, I mean, there may be many curves that can bring P to a point P prime that is near it. So so the problem is that there's many curves, and this means that the one-to-one mapping might seem to be an issue because it might be more like a one tangent vector maps to many curves, many equivalent curves. And the answer to solve that is actually through equivalence classes of curves, which we'll see later on. And in fact, that's one of the things we see in the definition of the tangent space on Wikipedia. Okay, so how do we construct this mapping? So when we have a curve, um, when we have a curve the manifold, um, let's say we have a curve on the manifold, and let's say there's a function. I'll just call it a temperature function. It can be any other function uh, that maps, that maps a point on the manifold to a real value. There's a real valued function on the manifold. What this allows us to do is it allows us to define gamma after it's more like what this allows us to do is define uh, T composed with gamma, and that is a map from 0, 1 to R. If we then take the derivative, so let's say the curve maps lambda to gamma of lambda, that allows us to take the derivative because it's a map from real numbers to real numbers. We can apply single variable calculus analysis to take the derivative of this T composed with gamma with respect to that parameter lambda. And yeah, and this is well defined. Um, so yeah, and this is well defined. So um, okay, so we can think of so essentially we can think of this. Essentially, we can think of let me change the color of my pen. Essentially, we can think of this d over d lambda as the definition of a tangent vector. And and um yeah, and the reason is because um yeah, we can think of this d over d lambda as a definition of a tangent vector. Uh, but a tangent vector can be expressed in terms of bases. So we have a question, what kind of basis will be represented over here? And the reason why we want to express the tangent vector in terms of basis is because uh, when we when we want to add vectors together, it's very natural to do them in terms of when there's a basis. So if we just have an abstract arrow plus an abstract arrow, in order to do calculations, we need to express this vector in terms of its basis, and the basis is a set of numbers, right? We can think of them as called a column of numbers and a column of numbers over here. And only when we have these columns of numbers can we say concretely that these two vectors added up together gives me some composite vector. There's a sum of both of them. So this is in some sense this is the abstract definition of a tangent vector. Um, so what can we do from here? We can we can uh we can what basis is most natural to this what basis is most natural for the tangent space? And it turned out the answer is actually partial derivatives. This will turn out to be the basis for our tangent space defined at point P. So what does this mean? So if going back to our picture of a manifold, we have a point P, and it's guaranteed that P is in some coordinate chart, and this coordinate chart is a homeomorphism, which means that there's a one-to-one mapping with RD, and the RD is basically a set of coordinates x mu, where mu ranges from 1 to d. Um, so we have we have our function t over here. When we compose phi inverse with t, this gives us a mapping from RD to R. And because this once again are real numbers are convenient because we can do multivariate calculus with them. We can take the partial derivative of that with respect to the input. So what this means is essentially, so this is well defined now. What it corresponds to is, imagine if we have a, how we can visualize this is that um we're asking that in this manifold, when there's a temperature function defined on everywhere on the manifold, if we start from a point P, we are P we are consider increasing um increasing the coordinate value for each one of them. So if increase the coordinate value for x1, and then it brings me along this coordinate. Increasing x1 would increasing each coordinate basically uh each coordinate basically defines a curve on the manifold as well, right? And increasing x2 may give me in this direction. And to give a concrete realization of that, consider polar coordinates where we have is a two-dimensional manifold. So if we have a point P over here, increasing in the r direction might give us this, and increasing in the theta direction might give us this. So this is a more concrete picture of what I've drawn over here. Um, yeah. If I so if I do that, increasing each coordinate and measuring the temperature, measuring how the temperature changes as I increase that coordinate, uh, is given by this partial derivative. And what can we do from here? We can see that if we take this definition and this definition and try to combine them, right, it's actually it's awesome because um, dt over d lambda, when done in multivariate calculus, we can think of this um, we can think of this part. So what we're essentially doing is we're applying a chain rule. And how can we apply the chain rule? When we consider these two tangent vectors, uh, we can consider a map. Okay, let me think how I can formulate. We can consider a map that maps from T uh R T to R. We can consider a map phi um T after this. I'm trying to make the multivariate calculus part rigorous. I'm trying to say something like RD to RD to R. I know, I know. Okay, so this map, when we have a map from this to R, we can actually factor it through. We can add an intermediate step that brings it to RD to R. And this map over here is T of uh this, and this map over here is T of gamma. So the overall map, oh wait, no, this is wrong. And this is the coordinate representation, which means that it is something's fishy over here. Um, gamma gamma after T, RD to T after gamma inverse, RD, this is the thing to, gamma to m, gamma to m, m to phi.
Right, yeah.
Yeah, that makes sense. This map is T after gamma. Wait, composition of maps. Oh. Yeah, yeah, okay. So essentially we can decompose T after gamma into T after phi inverse after phi after gamma. And now this one and this one is oops is this one and this one respectively, right? I'll probably have to do this a few more times to get it really smooth. Yeah. Okay, so this thing, yeah. So yeah, so that by doing since we have this, we can do the multivariate chain rule, which lets us decompose this derivative of t with respect to lambda into derivative of uh x. Okay, it's not a derivative, it's a full derivative of x mu with respect to lambda and dt over dx mu, where there's a summation over all the mu's there are. And what do we have over here? Um, we have we have a we have a vector. We have a vector, or rather, if I may edit it a bit, it's not the entire thing. I have a vector over here. These and it's a sum over. These are components, and this is a basis vector. And the t is can be replaced with any other function, right? But this entire identity over here will still hold true. Um, yeah. So what are the components? Their components are basically saying that if I have a curve, I'm asking how does each coordinate, right, change as I move along this this curve. Um, yeah, and that's pretty much the definition of um, and that's how you define tangent vectors in terms of that's how you define tangent spaces in terms of curves on a manifold. Yeah, now going back to this equivalence class thing to wrap things up. Um, we have we basically we to define this thing, we basically make an we make an equivalence relation between curves gamma and so we say that two curves what symbol do they use? So we say that two curves in order to make this rigorous, right? We still have the one to many curves issue. To make this rigorous, we have to define the equivalence relation between curve gamma 1 and gamma 2. And we basically say that they're equivalent if we basically say that they're equivalent if so let's say the parameters defined are lambda 1 for this one and lambda 2 for this one. Um, we basically say that two curves are equivalent if the derivative of gamma of any function, given any function t, we say that they're equivalent uh if and only if they are if they are derivatives of okay wait, I'm having some difficulties. Um, the tablet is having some
Oh no.
if Yeah, okay.
Okay, we're there.
Is this correct?
Yeah, yeah, I think so. I mean, it has to be right because like the two curves are basically have the same what directional derivative at the same points.
Hmm. I have a concern right now because I say that any function t for any function t, but what if they are equivalent for one function t but not for another function?
No, they'll be equivalent for all. So at the end of the day, you just really need if you really want you need to calculate that equation in like a specific coordinate system, and it'll all work out well because like it's basically equal to now like d x mu d lambda 1 d partial t partial equals dx mu d lambda 2 partial t partial x mu. So what you really need is for these two to be equivalent, which they are. So yeah.
Hmm. My concern right now is, oh, um, oh yeah, yeah. So this being equivalent, it implies that that implies strictly that this if is a if and only if
Yeah.
implies this, and now this right side is independent of any function I plug in, they will be equal. So if
Yeah.
these two
So yeah,
are okay, then
it
then
has to be true for all functions. That's how you get the IFF.
mm,
But it's just all common sense. So like
yeah, okay, okay, that makes a lot of sense. Yeah, I think I mean personally I've made my yeah, I've convinced myself of I've always wanted to make this video for quite a while. But I never really fully dived into it. And I think yeah, I felt like this was something where I derived the tangent space definition
yeah,
from first principles without much reference. Yeah, okay, that's great. Yeah, so in this podcast we managed to define tangent spaces.
right.
Are you tired?
No, like here's the thing, like I genuinely enjoy this.
Oh,
I have no
okay, that's
idea what
great.
we're
Yeah.
going to do next, because I have zero plans. I'm gonna do literally
Hmm.
whatever the hell comes to mind. So, um, yeah. I do have this like general idea that the whole objective is to do something related to quantum field theory, which I am
Hmm.
going to I do want to get there. However, for today, understanding tangent spaces and manifolds was extremely good. In fact, this I think is one of
Yeah,
the
it was fun.
more extremely important things that we need to do
Hmm.
before going into quantum field theory. Um, but
Yeah,
be prepared to expect a lot of things to go into various directions without ever
sure,
coming
sure.
to
Without
a
much structure.
reasonable conclusion. Okay, yeah.
Yeah, yeah, that's good.
But
I'm good with that.
I like how things are going. Like I think this is
Yeah.
genuinely very fun.
And it's very pedagogical for myself as
Yeah,
well. Yeah.
yeah, it's yeah, it's great. Yeah,
Mm. Oh yeah, regarding this is a small small side. One of the issues that you know when we have the this when we have this definition
yeah. Should I stop recording or should I keep recording?
no, you can continue.
Okay,
Uh, I can always cut it out. Yeah. And then the annoying thing is when we in the Lagrangian there's a term that looks like this.
right,
It's like minus 1/4. This is a free case. And there's of course the coupling to source.
right,
When we take the partial derivative of the Lagrangian with respect to something that I've always I mean I've done it before. When we do something like this, we we typically um we just typically say that this is f mu mu, right?
yeah,
Um, but something that I've always struggled with is that this factor of 1/4, I mean it disappears, and I know exactly how it disappears. The full way to do this is to okay, perhaps if we have a simpler example, this is something that I have in my field theory class when we have this, something like that. And if we want to take the if this is the Lagrangian, and we want to take the partial derivative of this with respect to the lower index, then actually the proper way to do it uh is to make sure that both of them have a lower index. So the fully rigorous way to do it is to make sure both of them have a lower index. Uh, yeah, and then from here, then I have the Iraq delta that contracts them together. Or for all purposes, actually, I can have this to be oh, actually, that's not quite right. It's more like the Minkowski metric. Yeah, right. Something like
Yeah.
this, and then now I apply the product rule, and then that's where I have actually to be honest, maybe this isn't the best because the indices don't make sense. So we fully proper, right? We should have something like that,
I
something
think like
like that, and then now we
usually the best way to like do these types of things one way to do it is to define stuff as like taking the partial derivative of the Lagrangian uh with respect to the covariant derivative of the field. That usually makes a bit more sense.
oh um
But
oh I
yeah,
see.
what it doesn't
Uh,
it's
can
not
you
a big
elaborate
deal.
more on that?
Uh,
Because everything I've done, I mean, I'm most comfortable with flat space like this. But yeah, I see your notes. You did it with the covariant derivative.
it
I'd
doesn't
like to know
matter.
more.
Like you could do either. Like
Um,
uh
in curve
generally
space.
uh generally uh whatever this is, it could be a vector field. It doesn't really matter. Generally, you have this, so it doesn't really matter. This is just neater.
Oh, in the case of curve space,
Yeah, it's the same.
is in curve space is both the same.
Yeah, because like go to locally flat coordinates, you'll see they're the same. Um,
Oh, I see.
like you could just check this. Like it's not really that important. Like it's just up to you which way you want to write the equations. Doesn't really matter.
I see. Okay. When we have okay, so is it right to say that the covariant derivative of any field can be a tensor field or anything is actually equivalent to a partial like this in locally flat coordinates?
Yeah,
Oh, okay. Mm, oh, in locally flat coordinates, in locally flat coordinates, the Christoffel symbols vanish, right?
yeah.
Okay, yeah, then that would make sense.
Like it's
Um,
really like just take an example Lagrangian and do the calculations. It will become immediately trivial. Like this is one of the things where explaining it is not very satisfactory. Like sometimes it's more
I
satisfactory to
see,
not explain something because
I
the
see,
explanation is very boring.
I see. In, in the case where if okay, we think try to think of this from what we're doing from a physicist overall perspective. When we have a field phi, we take the covariant derivative in like when we say we do theory in locally flat coordinates, um, if we think of this as a space, this thing is not a manifold. If we think of it as a space of all fields,
Yeah,
um, the trajectory of this field, uh, along the space of all fields, uh, um, yeah, okay, sure. I mean,
like it's not that it's not that complicated.
mm,
Like
sure, sure.
yeah, just do the calculations. Like
Okay.
because this is one of those cases where the you can you can do the calculations in a specific case and it just pertains all the complexities in the general case, so
Mm,
it doesn't really matter. Like
I see.
it's really a simple question. It's
Mm,
just neater if you do things with covariant derivatives because covariant derivatives are well defined, compared to just derivatives of tensor fields in a particular coordinate system. But I mean that's just to your aesthetic choice. Like at the end of the day, it doesn't matter how you calculate things; you just need the answer.
I see. So is it right to say that when we do it in a certain coordinate system, it's kind of like saying that the covariant derivative is coordinate independent, but when we choose a particular coordinate system, it's kind of saying we choose to work in this coordinate system. It's not
Yeah,
like
yeah,
saying,
that's pretty much it. But like,
I see, I
okay,
see.
so okay, I have this personal opinion on like the whole thing. When physicists like teach like general relativity or just relativity in general, they just really like to. So, one thing that has always kind of bugged me about the pedagogical methods of like teaching relativity is that they start with the SO31 invariance of Lorentzian of like special relativity, and they just try to move on to general relativity, and then they talk about this whole thing about being coordinate invariant and how important that is.
Hmm.
But in reality, the SO31 symmetry of special relativity is like a is basically invariance under the Poincare group. That's something that has to do with the isometries of the spacetime. Meanwhile,
Hmm.
coordinate invariance and general covariance and general relativity is just about it's really not about anything. It's almost a vacuous statement. Because like
Oh,
if you
hmm.
were to just define everything, if you were to just like define everything
Using
you should
covariant
never
derivative.
define something in like a particular coordinate system. Um,
I see, I see.
so in that case, it just becomes obvious if you just define everything correctly, it just becomes obvious that coordinate systems are just like tools that you can use at your preference, and it doesn't
Hmm.
really mean anything pedagogically to talk about general covariance that much. Um, but the thing
I
is
see.
that when people teach relativity, they have this concept of space-time isometry, SO31 isometry, and special relativity, and they just kind of try to squish it, like squish the arguments of SO31 invariance of basically relativity and special relativity. They kind of squish it into this general covariance argument in general relativity, which in my opinion muddles the logic a lot and makes things even more confusing. Um,
I
so uh,
see.
so yeah, my take is pretty practical. Coordinate systems are tools. Use them if you like. You can always use another
Hmm.
coordinate system to do the same calculations. Sometimes transferring between two different coordinate systems might be a pain in the butt to do the
Hmm.
calculations, but yeah, that's just pretty much
Hmm.
it.
Hmm.
And
I
like
see. So like,
there's nothing particularly, I don't know, that's just my take on general covariance.
I see.
It's just a bit of a red herring. But
It's a
yeah,
definition. It just lies in the definition. Like everything we define, the equations, they should be uh coordinate independent stuff, and then naturally
yeah,
the general covariance.
right, yeah.
Like it's not
So
really
in
an axiom.
yeah,
Yeah.
it's
Mm.
that yeah, it's not a guiding principle. It's just trivial.
I see.
But
Okay,
but
yeah,
in
that
like
makes sense.
in quantum gravity, diffeomorphisms end up being gauge symmetries, but that is a whole entire problem entirely, and that's just something that's a whole entire problem. So yeah,
Mm,
yeah. I mean, that's just really it. That's just yeah,
I see, I see. Okay, that's cool. Yeah. Uh, oh yeah. Anyway, yeah, I was just complaining a bit about this thing where actually, to be honest, besides this the Klein Gordon thing and this electromagnetism, I haven't really seen such. I mean, haven't really seen it appear anywhere else. But in general, I think it's just important to do this kind of derivation once in your life and
yeah.
form and
I mean, like you can
yeah.
always do it multiple times. Like it doesn't really matter. Like it doesn't really, it's not that important.
Yeah, okay. Um, uh, oh yeah, you said that you introduced quantum field theory uh, using um, and Noether symmetries, like using a
Yeah,
conservation of current.
yeah. We'll
I'll be
get
keen
there.
to hear more about that. Yeah.
Yeah, we'll get
Oh, okay.
there.
Could you give me a rough? Okay, sure.
No, I'm just going to talk about two things. You can derive very similar looking equations both in classical mechanics and in quantum field theory. In classical field theory, if you do a little bit of calculation, you can derive Noether's theorem from just like the classical equations of motion and etc. etc. In quantum field theory, you can use word identities to derive some similar things. And the interesting thing is that the path integral derivation, the path integral gives you this like word identity. Meanwhile, classical field theory gives you this kind of Noether theorem. And they look extremely similar, which is, I think, the most what which in my opinion is the most is one of the most compelling, at least at beginner level, is one of the most compelling arguments you could give for why the path integral gives a quantum field theory.
Oh, oh, okay.
So it's
Um,
entirely pedagogical. It's entirely pedagogical. Yeah.
I see. Okay. Why is it one of the most compelling reasons that path integral is a good way to quantize a field?
The here's the thing. Like the way things go in physics, you can calculate some things in the path integral. Um,
Hmm.
but the usual derivations of the path integral formalism from the canonical formalism in quantum field theory
Mm-hmm.
books are severely flawed,
Hmm.
for many, many
Oh.
reasons. Like the splitting of
Hmm.
time,
Hmm.
that's not rigorous at all. See, the
Oh,
whole
what
thing,
do you mean splitting of time?
like splitting time into infinitesimal sections and then doing the insertion of the bunch of like identity operators,
Hmm.
that type of stuff. That's
Hmm.
uh so that like that's so there are many many flaws. Like oh my God.
Hmm.
So the thing
Hmm.
is, even when those flaws exist, like people, okay, so the real reason, uh, this is the claim that I want to say, is that people are not
Hmm.
using the path integral because they derive that the path integral is equivalent to the canonical formalism. People use the path integral because it is approachable, and they calculate things at path integral, and then
Hmm.
they actually have to check that they agree with things in some canonical formalism. Sometimes they get the
Hmm.
canonical formalism by first calculating things in the path integral and then deriving the canonic and then getting some operator algebra from that. So
I see.
pedagogically, we might feel the urge to basically, when you introduce a new tool, you may find the urge to derive why that tool is useful before introducing it to your audience. But sometimes the tool just exists and people are using it. So sometimes you just really
Hmm.
have to focus on what is being done and what's coming out of it. Um,
I see.
yeah. So like, uh, I don't know. So like, but at the same time, like, so really, the path integral sometimes it might work, sometimes it might not. The path integral
Oh, what are
itself is
cases where it doesn't work?
well, I don't know, but I feel like it might be possible. The thing is, the path integral itself is not well defined to begin with. So what you really have,
Hmm.
what people really mean by path integral, they mean a collection of different toy models. The path integral is essentially a collection of different toy models that each have to be calculated in very different ways. That are individually well defined, but as a collective, there is no general definition of what they are. And
Oh.
for all the models, for most of the models, if you calculate the model, you get something that is basically a quantum field theory. But one should expect that there might be a pathological model where things don't work out. For example, and now that I think of it, there are examples of path integrals that calculate things that are not unitary quantum field theories. But in canonical
Oh, I
formalism,
see.
like you start with unitarity, so like a whole bunch of things can go wrong. So it's very
I
difficult
see.
to generalize, and any textbook argument is essentially flawed. So
I
uh
see. I see.
so it's really just vacuous pedagogical stuff, which is not
Hmm.
helpful in the long term.
Hmm. When I talk about the path integral, I'm just gonna add a link to, I just add a link to one of the derivations, the common ones, but I emphasize that if I can show you just like that, I emphasize that it's a hypothesis that uh this
Yeah.
path integral extends to all of physics because there's no reason why this derivation would apply to field theory,
I mean, you could do a
but
similar
it's more
thing,
like
but it's extremely
oh.
flawed. Yeah.
I see. So yeah, so I think there's a school of thought that says that path integral is kind of the fundamental object.
Yeah, yeah,
But
you could say that. Like, yeah, it is a school of thought. But
yeah.
people like like quantum field theory is a developing field and it does not have a definition.
Mm,
So
yeah.
when you're working with something that does not have a definition, um, the main thing is that you basically an object that does not have a definition is basically just a set of guidelines. So an object that doesn't
Mm,
have a definition is just a set of guidelines saying, I would really like it if whatever you're working on would satisfy these particular properties, which make it
mm,
attractive from my viewpoint. So what you would do is
mm,
you would have to come up with a model that is suitably well defined, and you just try to satisfy a few key properties which would give it that attractive quality, which is basically what quantum field theory research should be like and is like in my particular
mm.
opinion. Obviously, you
I
have
see.
particle physics going on, like phenomenology, but that's not really quantum field theory research. That's particle physics research, so that's a different thing. But
Mm.
like anyway, yeah.
You mentioned something about unitary quantum field theories. So unitary just means time evolution is re in some sense reversible, right? I mean, unitary just means
Like I didn't
this,
study
right?
it. Didn't study that topic enough to be well versed in it. I cannot explain. Like,
I see.
but
Okay.
things can happen and things can go wrong. Like
I see. I see. Okay, but I suppose those are generally at a higher level. Um,
some things happen. I don't
okay.
know what
Okay.
that is, but some things happen. That has always been the case. So
I see.
my approach to physics, especially these days, I have decided very much to accept the chaos, and I
Hmm.
have completely given up on trying to find any general or unified framework in order to understand the physics. Physics is a jumble of things. Uh,
Hmm.
Physics is a jumble of things that coexist together, and some of these things
Hmm.
actually contradict each other, but you just have to work with it because that's life. So
Hmm.
yeah, that's my current viewpoint of physics, and that's one of the reasons why for this particular podcast I do not aim to go anywhere. I'm literally
Hmm.
going to go here and there. I'm going to deal with a bunch of things that I can at least comfortably explain, but there is no
Hmm.
guarantee that that would lead to anything meaningful.
Hmm. Yeah. Sure. Um. Yeah. Okay. Um. After the so we have defined tangent spaces. Uh. What is the natural thing that comes after that?
I don't know. I'm not really feeling like I think I'm gonna mention metrics.
Hmm.
I'm not going to mention Christoffel symbols and covariant derivatives for a while. I think the
Hmm.
natural thing is obviously differential forms. Um,
Hmm.
so I might do metrics
Oh.
first,
Okay.
or I
Okay.
might do differential forms first. I think I'm going to do differential forms. And then later on, I'm going to introduce the metric when I talk about Hodge duals.
Hmm. Nice. Nice. All right. Do you want to begin now?
Oh, sorry.
Do you want to start talking about dual
Yeah, I think I'll do
concept?
that next time.
Okay, sure.
Hopefully you can edit something out of this. I feel like editing is a very non-trivial thing here. But hopefully you have the
Yeah,
experience. I personally don't. Okay.
I
Yeah.
think I'll probably yeah, I'll try to figure something out.
Yeah.
Yeah.
Okay. Anyways. Yeah. I'll stop the recording.